Hi, welcome back to this course. So we were discussing about different problems of random flights and random walks, and we sort of understood about unbiased random walks, and we were going through some examples. But in the last class, we talked about a few things, and there some difference equations were used, but some of you had some problems to tackle those things. So we will first try to see that how we can solve those things. Okay. So basically, when we are getting this kind of things, let's say you got this kind of expression, right? So difference equation is little bit different. So from here, how can you write this? Okay. So to write that, let's say Rn plus 1 is equal to 2 Rn minus 1. So basically solving difference equation. So whenever you solve the difference equations, you need to write the difference equation in a preceding terms. So our equation was R n plus 1 is equal to 2 Rn minus Rn minus 1. So the way to solve this, let's say you assume one solutions Rn plus 1 is R to the power n with some constant, right? Okay, so if you do that, or n plus 1 or Rn is equal to Rn, so you can get substitute here Rn plus 1 R to the power n, here R to the power n minus 1. So it is homogeneous in the sense if you can write all this power thing in one, just like a differential equations you can write in this expression. So it's a function of power of n and r, right? So now you can take r to the power n minus 1 common this side and becomes 2 minus 2r plus 1 equal to 0. And this thing, if you write, so this thing r square minus 2r plus 1 equal to 0, this thing is called characteristic equation. Okay, so if you solve it, for here this is r equal to 1, for both the roots are r equal to 1, so then it becomes n equal to, then, so basically you write here r equal to, so basically it becomes 1 to the power n, right? But so for a like if you talk about a common thing, then this expression, let's say Rn, it's, let's say, alpha for a homogeneous thing plus alpha Rn minus 1. So basically you write in terms of Rn minus 2 equal to 0. This is a homogeneous equations. So basically you can write this like this, r n minus 2 as r square plus alpha r plus beta equal to 0. So you can get and solve these characteristic equations, and we can get 2 root r, 2 root r equal to n1 and n2. Then you can get expression r from uh, r1 to the power, let's say, n1 and r to the power n2. Okay, so basically what you are doing, you sort of solving these things in this way. So basically your 2 root r1 and r2 becomes n plus b r2 n, like this. So we never worried about this term because you can add these things. But whenever you will get two equal roots, then your characteristic equations will have solutions like this. So let's say this is the thing, then r to the power n will be a plus, here the value of r, there will be extra n, r to the power n, for a same, let's say same solutions that we have done here. But in this case, when there was a inhomogeneous term there, -2 was there, so there was extra -2, so we cannot write xn plus 1 minus 2xn plus xn minus 1 equal to 0. That is called inhomogeneous term, just like a differential equation. So there you, so in, if in a differential equation there is inhomogeneous term, what you should do, you have to first write the particular solutions of this. So that's why we used this polynomial form. So if you say different polynomial forms, so for this form and this form it will not satisfy, for this thing it will satisfy, and from there you can get this value. So basically I wanted to discuss about these things because since in our, like in physics, people are not sort of trained in difference equations. Okay, so what we are discussing, we got the probability equations for this biased random walk. So basically then we got, this, let's say, so the probability relation was Rn is equal to P Rn plus 1 plus 1 minus P R n minus 1. So we will try to solve it. Okay, so to solve it, what we will do, we will use the boundary conditions or the initial conditions. The boundary conditions was that, so if it is like total amount of wealth is 0, then you will quit the game, and if it is reaches its target W, then also he will, sort of, there is no need to do that, so he will be RW is equal to 1, because that's what we have done to this problem, because this sort of mapped to these things, okay, 0 to 1, like this. So okay, now we will rearrange these things because we have to write in terms of this. So then P R n plus 1 becomes minus Rn plus 1 minus P R n minus 1 equal to 0 for n is between 0 to W. Now you can write the characteristic equations, the characteristic equation for this recurrence relation will be, so for, since it is 2 times more, so this will be px square minus x, x plus 1 minus p equals to 0. So basically if you solve it, then your solution becomes, so the quadratic formula, we call it Siddharacharya's formula. So quadratic formula gives us the solution, x is equal to, so minus of b, this one, so this will be 1, plus minus b square, that will be 1, minus 4ac. So let's say this is ax square minus bx plus c equal to 0, if you write like this. So this will be minus 4 times p times 1 minus p divided by 2a. So this will be 2p, right? So solving this, you will get 1 plus minus root over of 1 minus 4p plus 4p square by 2p. Basically, you will get 1 plus minus 1 minus 2p whole square by 2p, right? And you get it like this: 1 plus minus 1 minus 2p by 2p. So if it is plus, then it becomes, if it is plus, then it becomes 2 into 1 minus p by 2p, or if it is minus, then it will be 1, right? So basically it becomes 1 minus p by p, or 1. So there are two roots of these things. So there are some important insights here. From these roots is that if the gambler if the gambler is equally likely equally likely to win or lose each bet, which was the unbiased thing, then p becomes half, right? Then this 1 minus p by p will have the, so let's say I can write it as q by p. So if q equal to p, then this will have same root, right? So then the characteristic equation has a double root at r equal to 1, sorry, at x equal to 1 we have. So this situation is earlier addressed, so you will not worry about it. So we will get to a double root. It's a double root, so we'll consider about double root only, because single root we have discussed earlier. So for double root lead to the solution that Rn is equal to a plus b r to the power n. So let's say this is equation number 3. Okay. So now since this has so for a double root case, this will be sorry, for double root case, when the same double root, so that case becomes a plus b n into 1 to the power n. But since these are two different roots, this case roots are different, so we will use this relation, like this relation, a r1 to the power n r to the power n. So then Rn becomes a first root to the power n. So first root is 1 minus p into p to the power n plus second root b into 1 to the power n. So in this direction you can see that how these two solutions are different. So from this way we can sort of comment that how, if the game is fair and if the game is not fair, then that can give two hugely different result. Okay, so in one case you can get, in one case you get nice linear solution, and in another case, in other case you get exponential solution. So you can get two different solutions depending upon your biasness. Okay, so 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 that's why the game is not always fair, and that is also true in the game of life. Okay, so now if you use now apply, so the boundary conditions, now applying boundary conditions, boundary conditions boundary conditions into this general form, into this general form of the solution, you can get a linear of solutions. So first, r0 was 0, so if you substitute this value, so r0 was 0, so if you substitute this, a plus b becomes 0, and rw was 1, that makes a times 1 minus p by p w plus b was 1. Now you need to solve these equations. So basically, if you get this, then it becomes a. So let's say you subtract from this to this, then a. So this is equation 1, this is equation 2. So a times 1 minus p by p to the power w minus 1 was 1. From here you get a is equal to 1 by 1 minus p by p w minus 1, and b becomes, b is minus of a, so b is then minus of 1 by 1 minus p by p to the power w minus 1. So you get two coefficients from these expressions. So substitute, if you substitute this value, so substituting these values back into the problem, solution, will get r to the power n was a times 1 minus p to the power n, so that becomes 1 by 1 minus p by p to the power w minus 1 into 1 minus p by p to the power n minus minus minus, so plus b, so b means minus of this, so this will be 1 by 1 minus p by p w minus 1. So basically if you take out this value, then it becomes 1 minus p by p to the power n minus 1 divided by 1 minus p by p w minus 1. So from here you can see that it's not so trivial. So the earlier assumptions were like just up until like it was totally bestowed on the fate of this thing. So this is after all not so uh, simple. Okay, so we can see here, we can comment here that if the gambler, if the gambler starts with in rupees and wins each each bet with probability p, then the probability then the probability lux, because our gambler names was lux, the probability lux reaches w, which is his aim, rupees, before going broke, before going broke is 1 minus p by p to the power n minus 1 into 1 minus p by p w minus 1, because that is the our probability of, we have defined Rn as like this. So we define Rn as that probability, right, that the goes home a winner, right, with this money w. Okay, so that is like these things. So now if the game is biased against the gambler, then there was 1 minus p is greater than p. P is the probability probability he wins. That is the main case. That means if n, that means if n, his starting wealth is starting wealth is also reasonably large, then both exponentiated functions are big numbers, so then the amount by which you are playing this game, that does not make that much difference. So this each betting amount, which is 1 rupee, does not make any difference. Okay, so that means her probability of reaching W dollars is very close to all these things. Okay, that means, so this term will be much more than this. So basically then it becomes that 1 minus p, so you can take this out, -1, so basically it becomes 1 minus p by p times n minus w, and n minus w is m, so 1 minus p by p times m to the power m. Okay, that means if he is hoping to come out, let's say 100 rupees ahead, then it's p, so let's say his p is around 18 by 38, so his probability of success is 1 minus p, so 1 minus p, then it will be 20 by 38, and this will be 18 by 38 to the power minus 100, right? Because uh, p is in this case the probability of winning. So which is in that range, it becomes 9. uh, that makes 1 in 37,648.62, like this number. So basically, if it is also starts with $1 trillion, she is not likely to ever get more than 100 rupees, because you understand this point. So you need to win more money that you are putting on, right? So basically, if you put 100, if you put $1 million, $1 trillion also, and you want to get 100 rupees more, then then this will be uh, the probability of its reaching the $W will be like this. So where 1 minus p will be like this. So p is its probability wins. So you can get that this value is, sorry, this is minus m, this is minus m. So from here you can get this. So even if even if even if he starts with $1 trillion dollar, he is not he is not likely to ever get ahead by 10 rupees. Trillion rupees, let me write it. Trillion rupees. Okay. So basically, you are sort of, so your chance of winning is very less. But but understand one point, that why it's happening. Why it's happening. So why is it so? You need to understand that why it is happening like this, right? So for that is that, so you can understand that gamblers starting wealth have or has rather has so little impact, so little impact on his probability probability of coming out ahead is very little impact, right? So to understand that, we have to first see what are the two most reckoning force here. Okay, so first most important thing here, most two important things here are first these things that gambler's wealth has random upward upward and downward movement, since he is losing some money and winning some money, swings. Okay, okay, so due to its good fortune and bad fortune. Okay, and second thing is, if you see about the main thing, that his his wealth has a has a steady downward downward drift downward drift because you have to understand one thing, because he has a small expected loss on every bit. So there are like small expected, so the expected loss of every bit is small. So you can see here, let's say, so no matter how, so this is, let's say, gambler's wealth, and this is time, and this is the W where it will cut off. So let's say it starts from year in. So let's say this. Although there is some upward movement, so although there is always some steady drift. Okay, so since it has a steady downward drift, So he has a small loss or expected small loss on every bet. Okay, so to understand it more, we can say these things. So gambler gambler wins a rupee. Gambler wins a rupee with probability 18 by 38, and it loses a rupee with probability 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 20 by 38. So the expected return is expected return on each bet is 1 times 18 by 38 plus minus 1 times 20 by 38. Now if you do that, then it becomes minus 2 by 38. That means it's losing money. That means minus 1 by 19. So it's very small. The net loss is very small, but it has a drift in that thing, right? So his wealth drifts downwards by a little over 5 paise per bit. So we can get a drift. Okay, so now you can see, let's say, what if that gambler starts with $1 billion, okay, or billion rupees. So you will play for a long time, right? Let's say you try to play this game for a longer time, because more money means you will buy more time, right? So if someone thinks that if one thinks that if he starts with more money with more money and he will play for a longer time, so at some point, so at some point C or he rather should have C he should have a lucky lucky upward swing that puts him puts him 100 rupees ahead. Okay, but the main problem is her or his total money is constantly, you know, going downwards. So problem is that main problem is main problem is that his wealth is steadily. So try to understand this fact and try to appreciate this thing, that whether where it is sort of interesting. Okay, so the wealth is steadily drifting downward, drifting downward. So basically, after some time, it drifts so much down that to get to that amount, here when he needs a much more longer jumps. So now, 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 to gain a dollar, he needs he needs a huge upward movement, huge upward swing, swing to save himself. So as time progresses, he needs much more longer jumps, and those huge swing, those huge swing is extremely, extremely improbable, improbable. So if so, probabilistically saying, there will be much lesser probability of getting those terms. So as a rule of thumb, as a rule of thumb, drift dominates swings over the long run. So if you are in stock market or financial market, or in kind of some kind of a climate or this kind of predictions, so you can think about it, and this sort of makes you intelligent, and also this sort of gives you that you know Jane perspective that what you should do. Okay, now let me get to another thing, that is the expected playing time, because from expected playing time you will get the okay. So let us assume, let xn be the expected number of bits, expected number of bits before going home. So this is the number of bits before going home. That means you are either broke or a winner. Okay, so now you got this, setting up the same recurrence for xn, you can get. So let's say if it is 0, that means if you are broke, then your expectancy is 0, you are lost, you have lost all the money, and your xw will be uh, also 0. Means if you start from here, let's say 0, if you start from here w, that means there is no need to play. So there is no need, so you are not playing, because if you are broke at the first instant of time, then why should you play? And if you are if you are winner at first instant of time, if you have that money, then why should you play? That is the intelligent this expectation time. And xn then must be first game you should play, so first one you should play. So at, let's say if you start from here, and xn minus 1, if you are here and if you are here, this is n minus 1, let's say this is n plus 1. So from n plus 1 to n come to here, you have to lose some money. So, and from here to here, you are gaining some money. So from to lose some money, that means the probability associated with this is 1 minus p. No, here the thing is, since you are at n, so either at, so either from here you will go to this. So what will be the time of things? So you, if your expectation time is this, then either you will getting the money or you are losing the money. So if you are getting the money, that means at n plus 1 uh, you are there. So then one thing is 1 minus p times xn minus 1 plus p times xn plus 1. So this is similar to those, that cliff problem. If you go here, there also we write the expectations here, like this one, right? So So when it starts so towards left, then he reaches to n minus 1. So if it is if it so it can go, it can lose some money or it can win some money. Okay, if it is win some money, then he will go towards that. So let's say what I'm trying to mean. So at next step, if it is win, so you will go towards this, towards the uh, cliff of this is this thing. And if it is, if he loses some money, then he will be going towards the broke region. So that is the probability 1 minus p, and winning some money is p, right? So that's the thing. Okay, so you gotta get this relation. So this is 1. Okay, so now this is similar as the solutions we got for this one, but here we have the inhomogeneous part here. So for that we need to do something. So this is similar to the previous recursion relation, except here an inhomogeneous part is present. So now we need to solve it. Okay, so to solve it, what we will do, so we can try with different particular solutions. So we have to find different particular solution where xn, let's say c, just constant, this will not work. And let's say if it is xn c plus d n, this tells this will work if p is as long as p not equal to half. So if p is half, then there will be like similar to the biased unbiased problem. So now if you plug this problem, so here we will just talk about the this thing. So if you plug it in this relation, then this is c plus dn, this is 1, this is 1 minus p times c plus d of n minus n plus p of c plus d times n plus 1. That makes it c plus dn is equal to 1 plus, let's say there is c, there is pc, so 1 minus pc and pc, that makes c, and 1 minus p into d minus n minus 1, 1 and p. So from here you can write, so for n it will be dn will be 1 minus p plus p. For d, it will be pd, and it will be minus 1 minus pd, and there will be a one there. Okay, so C cancels out, dn cancels out. Only thing remains is PD and plus PD, so minus D. So that becomes 1 is equal to 1 is equal to D times 1 minus P minus P. That makes D is equal to 1 by 1 minus 2P. 1 by 1 minus 2P. So basically, if you do these things, you'll get this. So now if you set, since C is arbitrary, since C is constant is arbitrary. So and if you put C equal to 0, then our particular solution, which is called it PI, particular solution, which is our PI, that becomes xn is equal to n by, so this was C plus dn, so d is this, so 1 minus 2p. So this is equation number 1. Let's say this is equation number A1, and the characteristic equation of this was similar. So the characteristic equation was similar. The characteristic equation is similar to the previous problem of Rn. From here we can write px square minus x plus 1 minus p is equals to 0, and we have already determined the roots. So x was 1 minus p by p and 1. So the general solution of this, general solution of this was xn is equal to a times 1 minus p by p to the power n plus b, just constant, plus this particular form, so there needs to be there, so n by 1 minus 2p. Now you have to put the boundary condition. So this is, let me write it as a2. Okay, so now if you put this, then for first condition is x0 is equal to 0, that makes it 0 is equal to x0 n equal to 0, so this will be 1 and this will be 0, so a plus b and xw is equal to 0, so 0 is equal to a times 1 minus p by p w plus b plus w is equal to 1 minus 2p, 1 minus 2p. So from here you can easily write the equation. So if you take it minus, so b cancels out and a is equal to minus mhm, minus w by 1 minus 2p divided by 1 minus p by p times w minus 1, and b is equal to w by 1 minus 2p divided by 1 minus p by p to the power w minus 1. So this is a3. So now, since you have got this ab, now we can easily write the final solution of this problem. So basically you can write easily xn is equal to this is a, you can write there, minus w by 1 minus 2p into 1 minus p by p to the power n divided by 1 minus p by p into w minus 1 plus w by 1 minus 2p divided by 1 minus p by p into w minus 1 plus n by 1 minus 2p. Okay. Okay, so basically now you can take out these things. So w1 minus 2p you can take out. So you can write n by 1 minus 2p minus w by 1 minus 2p is equal to 1 minus p by p to the power w minus 1 into 1 minus p by p into n minus 1. So now this is a complicated equations, but you can simplify it, right? So this is a complicated equations. Let's say this is w. So for a, let's say if, take a guess, let's say if m, which is w minus n, is large. If is large, then since p is less than half, and if p is less than half, then 1 minus p by p is greater than 1, and for large m, limit m tends to infinity, you can sort of get this thing. For large m tends to infinity, then it becomes this. I am talking about this term. So w by 1 minus 2p, w by 1 minus 2p times w by 1 minus 2p times, now think about this term, 1 minus p by p to the power n minus 1, 1 minus p by p to the power w minus 1 is equal to, now this term, if it is large, so then this term will be sort of 1 will not have any meaning, right? So, for this case you can then write that means case large, that means limit m tends to infinity w by 1 minus 2p times 1 minus p by p minus m equals to 0. Why 0? Because m tends to infinity means this term, this is constant, so this term sort of goes to 0, right? Okay, so because it's falling very rapidly, and 1 minus p by p, that will be greater than 1, right? So 0, that means as m tends to infinity, as m gets large, xn then becomes on this term n by 1 minus 2p, n by 1 minus 2p. So this is happening like so. This is a probabilistic viewpoint. So this means, what does it mean is, this is a5, if the gambler if the gambler starts with n rupees, she will expect to make about n by 1 minus 2p bets before she goes home broke, because you understand that she expects to lose. So sorry, let's see. So the expectation of losing of money, losing at each bet was 1 into 1 minus p plus minus 1 into p. So that was 1 minus 2p. So 1 minus 2p amount of money he is expecting to lose at each step. So basically that will be the case. So if it is getting that much money, so each step, so to sort of finish the whole n amount money, he needs this amount of bet on an average, right? Now there is a catch to this. I will This should be categorically mentioned, so that you guys cannot mistakenly think like this. Here, like, careful, careful, you can easily make those simpler statements that you can expect to have this amount of beds before going home, but this kind of argument is not correct. Okay, so because these are examples, these are examples where the expected duration of process expected duration of process is not close to the starting point, not starting point divided by starting point divided by the expected decrease at each step. So this expected duration of process is not close to the starting point, because we have just used some limits of these problems. Okay, so basically this is an interesting problem to think about, that what will happen if you think this whole gambling scenarios from a random walk perspective, and you will get the the physics or statistical physics is like yelling at you to know, okay, so let's see, this is the main theme, this is the main crux of the study. So you should uh, follow these things, you should think about it before guessing some things. Okay, so these are some interesting points, because you can see and that. So here, mm, means, let's say here, the whatever we have whatever calculations we have done, we assume that the number of duration of process like n is not like is not very much close to the starting point divided the expected decrease, because you can understand here we take m to be very large. Okay, so since we took n to be very large, so like you can say, like here the total number of steps is not like close to this n by 1 minus 2p states. So that's why you can get this idea. Okay, so I will stop here, and we will discuss next topic in the next class.